What are the chances of that? This is something you might have found yourself or someone else exclaiming at times when you suspect that something is more than just a coincidence. So we'll look at the 1969 Vietnam War draft as an example. In this, the birthdays were represented by numbers 1 through 366, so that's all days of the year, including our February 29th, even though this only occurs once every 4 years. The slips of paper were placed in capsules mixed in a shoebox, and then the capsules were poured into a deep glass jar. Then they're just pulled from the top because the assumption is that they're mixed properly at this point, and this is theoretically a valid way of getting a simple random sample. So we're going to address the question of whether they really were mixed properly. We got 25 December birthdays. So the proportion of all 194 birthdays drawn that were in December, this is a sample proportion, so we'll call that p hat, and that is the 25 December birthdays divided by the total number of birthdays drawn, and this comes out to be about 0.129, so very close to 13% of the drawn values were December birthdays. We're going to compare this to the population parameter p, or use this to estimate the population parameter p. This one is a little bit hypothetical of a population parameter, so I've gone ahead and defined it for you. It's the proportion of December birthdays that this method of mixing would be expected to produce on average. So what we're getting at is, was this an unusually high number of December birthdays just because that sample statistic happened to come out high by luck of the draw? Or if the question is about p, the population parameter, is this method of mixing going to always generate too many December birthdays? Maybe not always, but on average tend to generate too many December birthdays. So keep in mind that this population parameter is unknown. We don't know the value of p, and all of our speculation has to do with p based on the only thing we know, which is p hat. So we get to what we call the null parameter. This name will make a little bit more sense after we state hypotheses. That's what number we would expect p to equal if the dates were mixed properly. Now, if the dates were mixed properly, then we would figure there's 31 days in December. There were 366 days total. We should get this same proportion drawn for December on average, right? This comes out to be about 0.085, by the way. So we can already tell that our p hat, our sample statistic, looks a little high. This 0.129 looks a little high. What we haven't addressed yet is it too high, or was that just the luck of the draw, right? You're generally not going to find that this value comes out to be exactly equal to your null parameter, even if there's nothing really going on. The question is it far enough away that we could no longer just explain it by the luck of the draw? And so we get to hypotheses. The null hypothesis is what we would refer to as the status quo or no effect, and the null hypothesis starts to make a little more sense after we've seen a few examples. In this case, it would mean the dates were mixed properly. Now, the alternative hypothesis should be something contradictory to the null hypothesis. The alternative hypothesis in this case is what we are testing. What we are testing is the question of whether the proportion of December birthdays is higher than it would be if the dates were mixed properly. So in this case, what we're really suggesting is that the method of mixing favors December birthdays. So these are our two hypotheses. The null hypothesis, dates are mixed properly, nothing wrong with this method. Alternative hypothesis, this method of mixing favors December birthdays. And now we can make a little bit more sense of this language null parameter. null parameter goes with null hypothesis, right? It's the value of the parameter p if the null hypothesis is true, right? So if the null hypothesis is true, then p is equal to 0.085. But we don't know the actual value of p. This is just speculation. So I'm going to write these hypotheses instead of using words, using symbols. My null hypothesis is that this value p, my population parameter, is equal to 0.085. They were mixed properly. If we were to do this over and over again, maybe we'd find on average that it really does come out to be about 0.085. And the alternative hypothesis is that, in fact, this favors December birthdays, so on average we're going to see p come out to be bigger than 0.085. To test these hypotheses, we're going to look at a distribution that is called a randomization distribution. A randomization distribution represents possible values of the sample statistic. In this case, we're talking about p hat under the null hypothesis. And when I say under the null hypothesis, what I mean is assuming that the null hypothesis H0 is true. So this is a little bit different from a bootstrap distribution. A bootstrap distribution does not have a null hypothesis. Everything is based on the sample statistic. We just take lots of possible values of that sample statistic based on the only thing we know, which is our sample statistic. Here we also have a null hypothesis. So notice that the center of this distribution is at that null parameter value of 0.085, not at our sample statistic, which was 0.129. So it is, the distribution is centered at the null parameter. Like a bootstrap distribution, each dot is a value of p hat that is based on the null hypothesis being true. So we could say, for example, we can run a simulation and suppose that everything is perfectly mixed. Let's just draw a bunch of random samples of size 194 that we know really are random and see what values we get for p hat, where p hat is the same definition. It's the percent or the proportion of December birthdays. So each of these is a value of p hat, which is a proportion of December birthdays, calculated on the null hypothesis that everything is mixed properly. And we can see the approximate distribution based on the null hypothesis. Now let's mark our sample proportion here. That was 0.129. So our sample is here. It's about 0.13, right? So that's going to be very close to halfway between 0.12 and 0.14. So p hat equals 0.129. This is from our sample. And looking at it in this distribution, we're going to answer the question, does this seem like an unlikely observation? Well, likely observations are the ones that are in the mainstream, right? Here's a cluster of values close to the center. I could have made this a little bigger, right? This is just getting at the basic idea. Anything that's close to the center and close to the mass of the distribution is definitely not something we would call an unlikely observation. But the further out we get into the tails, so out to the right tail or out to the left tail, these are the ones we would consider to be unlikely observations. Here I can see that I only have one value that is more extreme than mine? So I would say yes. Only one value of p hat is more extreme than what I saw in my sample. And to just be clear about the different ways I'm using p hat, some of these are hypothetical p hats from the randomization distribution based on the null hypothesis. The one in purple here, this is the only one that really comes from our sample, right? So we're looking at our p hat in a distribution of hypothetical p hats. And this question leads us to what we call a p-value. A p-value is calculated assuming the null hypothesis is true, which means that we can use the distribution we have above. So we can use a randomization distribution. And it's the probability of observing a statistic equal to or more extreme than the observed value. So in this case, what that means is we saw that one value was more extreme than ours. That was out of, have to back up for a second, that was out of 100 samples. So I have to look at this here too. So we're looking at a 1 in 100 kind of situation. So 1 out of 100 was more extreme. That suggests that I should say 1 out of 100 as in division, which is equal to 0.01, or if we're talking about it, we might just say a 1% chance. So let's interpret this p-value now. We've said that it's calculated assuming that the null hypothesis is true. In our situation, the null hypothesis is true. That's equivalent to the dates were mixed properly. So assuming that the dates were mixed properly, the chance of observing our sample statistic, which is that p hat equals 0.129, or something more extreme is 0.01. Or we could say 1% if we wanted to here. So we want to think about, does a large p-value or a small p-value give us evidence against the null hypothesis? To answer this, it's helpful to think about what we call in logic a contrapositive. I might say, if it's raining outside, then I'm going to see people walking around with umbrellas and a gray sky, and the sun won't be shining. I look out the window, I see the sun is shining, the sky is not gray, and people are not walking around with umbrellas. And I say, I think it's not raining, right? So it's backing up the logic. Here we say, if it's true that the dates are mixed properly, then we expect to see a value that is fairly close to our null parameter. The chance of seeing something this extreme is very, very low, and therefore a small p-value, right? This gives us a small p-value, and so it seems like seeing something very far from center is evidence that the null hypothesis is false. So a small p-value is evidence against the null hypothesis. And in fact, the smaller the better in general. Well, better being subjective, of course, but the stronger the evidence. You can also think of the p-value as some sort of measure of how far apart your null parameter and your sample statistic really are in the context of the sampling distribution for that population parameter, which we're estimating with this randomization distribution. Of course, that's a whole lot of statistical language, so sometimes a picture's worth 1,000 words, right? We can look back at this picture and see if the dates are mixed properly, we really expect to see values close to concentrated at the center. When we start to see values more out in the tails, that gives us a smaller p-value, and it gives us stronger evidence against that null hypothesis. Now, something that I will mention just because I think it deserves mention before we leave this example and this picture, the actual p-value is probably smaller than 1% for this particular problem. And the reason is that this randomization dot plot is generated with replacement, but our actual sample, if we think about how it was drawn going back to the description, this was not drawn with replacement. And so our chance of getting another December birthday should have been getting smaller each time as we generated more and more December birthdays. I mean, look, we got 25 of them. There's only 31 December birthdays total, so the highest value I could have possibly gotten for p hat isn't even much higher than what I got. It would have been 31 out of 194. So it's not totally accurate to calculate a p-value using a simulation with replacement in this situation, but it does give us an upper bound on the p-value. Now, this is getting much more mathematical than anything that we're going to really hold students responsible for in this course, but I just want to say it before we end this lecture. It's really a much smaller p-value than 1%, but these methods at least can give us reason to believe that it is not more than 1%.